Previously, we learned to solve systems of linear equations of the form ax plus by equals c and dx plus ey equals f. Solutions to a system of equations are pairs of numbers x and y that make both equations true simultaneously. Since a solution makes both equations true, it's a point on both graphs. In other words, we can graphically interpret a solution to a linear system of equations as the point of intersection of the lines given by the two equations. But how do we find what those solutions are? To solve systems of linear equations, we use the substitution method and the elimination method. We'll now use similar ideas to solve systems of equations which are not necessarily lines. In other words, nonlinear systems of equations. As with solving systems of linear equations, where their solution is the point of intersection, when we solve systems of equations of any form y equals f of x and y equals g of x, then their graphs may intersect as well, and we can graphically interpret solutions to the system of equations as points of intersections of the graph. If the graphs don't intersect, we simply don't have any solutions to the system of equations. And notice here, when the graphs are not lines, that we may have multiple points of intersection, and thus multiple solutions that make both equations true. To find what these solutions, or points of intersection, are, we will frequently find solutions using the substitution method. Because at a shared point, the y value on the red curve is equal to the y value on the blue curve. And using the functions of the red and blue curves, we're left with an equation in just one variable x, f of x equals g of x, which we've spent all semester learning how to solve. And once we figure out the value of x, we can find the value of y by evaluating either function at that value of x, much like we did in systems of linear equations.